Okay, so here we've got two very interesting related sequences, an and gn. So if you start with two distinct positive numbers, x and y, basically your a sequence you start at x, your g sequence you start at y. Then to find the next term in your a sequence, you find the arithmetic mean of the previous term in each sequence. And then to find the next term in the g sequence, you find the geometric mean of the previous term in each of the sequences. So for example, a1, this will be x plus y over 2, the arithmetic mean of x and y. Then g of 1, this would be the geometric mean of x and y, so the square root of x multiplied by y. So we're going to be interested in what happens as n goes to infinity for these two sequences. But just before we deal with that limit, we'll have a look at a couple of properties. So the first of which we're going to prove is that for all n greater than or equal to 0, a of n plus 1 is strictly greater than g of n plus 1. So you'll note here we're starting with a1 and g1 because we don't know if x is bigger than y. Okay, let's prove this. So how we're going to approach this is we can look at what is an plus 1, this is an plus gn over 2. What is g of n plus 1? This is the square root of an gn. I'm going to begin just by writing out an plus gn all squared. Then I'm going to do some algebra, rewrite this, get an inequality, and then I'll be able to show, rearranging this, that an plus 1 is indeed greater than gn plus 1. The first thing I'm going to do is just expand this. So an squared plus gn squared plus 2 an gn. And then the next step I'm going to use, it's a bit of a trick here, I'm going to rewrite 2 an gn as minus 2 an gn plus 4 an gn. So why on earth am I doing this? It'll become clear in the next step. If I write this out then as an squared plus gn squared minus 2 an gn plus 4 an gn. Well, this thing here now, an squared plus gn squared minus 2 an gn, all this is the square of the difference between an and gn. So an minus gn all squared. Then we've still got this plus 4 an gn. Okay, so what we need to do next then is, you'll notice, for example, with a0 and g0, these are x and y, these are distinct, so a0 minus g0 squared, this is always going to be strictly greater than 0. And similarly, you can show that actually for every single term, an and gn aren't going to be equal if you start with distinct numbers x and y. So this is why we specify that x is not equal to y there. So this is strictly greater than 0, which means then that an plus gn all squared is strictly greater than 4 an gn. Okay, so what have we shown here? We have shown that an plus gn all squared is strictly greater than 4 an gn. So then what we can do, because an and gn, we start with two positive numbers, x and y, and then our a sequence, we're just adding together two positive numbers, finding the arithmetic mean of those, and here we're finding the positive square root of the product of some positive numbers. So you'll always get something positive, so we can take the square roots of both sides here. We get an plus gn is strictly greater than the square root of all of this, which is 2 root an gn. And then we're almost in this sort of form with an plus gn over 2, square root of an gn. We divide both sides by 2, an plus gn over 2. This is strictly greater than the square root of an gn, product there. And of course this means that an plus 1 is strictly greater than gn plus 1, which is what we were trying to prove there. So this inequality, the fact that an plus 1 is strictly greater than gn plus 1, this is actually a consequence of a more general result where if you have any collection of numbers, so long as the geometric mean, the arithmetic mean are both well defined for these numbers, then as long as all those numbers aren't equal to each other, then the arithmetic mean will always be strictly greater than the geometric mean. So I guess we could have been a little bit more rigorous dealing with the strict inequality here, perhaps using proof by induction. You can have a look at that if you're interested. So we're almost ready now to deal with limits as n goes to infinity of these two sequences. But first, we'll just have a look at the following property, which is that for all n greater than or equal to 1, we're going to have a go at proving that Gn is strictly less than Gn plus 1, which is strictly less than An plus 1 is strictly less than An. So what this means is our sequence G is actually a strictly increasing sequence, and our sequence A, as you go from the nth term to the n minus 1th term, you're going down, and this is a strictly decreasing sequence. So this will turn out to be really useful. So let's have a go at proving this. So first of all, you notice actually we've already done one of the inequalities, so I'll tick that off. We know that Gn plus 1 is strictly less than An plus 1. So now let's try and show that Gn plus 1 is strictly greater than Gn. So let's write out what is Gn plus 1. Well, this is the square root of An multiplied by Gn. And here we actually know that An is greater than Gn. And what we can do then is replace this An by a Gn. And what we'll get is Gn multiplied by Gn. So here, because we know that An is greater than Gn, replace this, we get a strict inequality. This here is just Gn squared. The square root of that gives us Gn. So Gn plus 1 is indeed strictly greater than Gn. So I'll tick this one off. And then we can use a similar kind of approach for the inequality with An and An plus 1. So what is An plus 1? This is the arithmetic mean of the previous two terms, An plus Gn. Divide this by 2. And then, because we know that Gn is less than An, we can replace Gn by an An here. We'll get a strict inequality. So here, Gn, replace this by an An. I know that Gn is strictly less than An. And then what do I get? An plus 1 is strictly less than this thing, which is just 2An over 2, which is An. So that's what we were trying to prove there. So I can tick this off, and then we've shown all of these inequalities hold. So now let's put this inequality to use. So the first thing I'm going to do is draw out what's going on here. So let's assume that x is greater than y. So we'll deal with the other case in a sec. But if we assume that x is greater than y, let's just have a look on a number line between y and x, what's happening with our An and our Gn sequence. Well, we know that A0 is equal to x, and we know that A1 is the arithmetic mean of these two. We know that G0 is equal to y, and then we know that G1 is the geometric mean of y and x. This is somewhere between G0 and A1. So we're using these inequalities here. And then if we want to find the next term, if we want to find A2, this is just the arithmetic mean. It's halfway between G1 and A1. So A2 goes here. And then to find G2, this is going to be somewhere between these, so maybe it's around here. So the kind of structure that we're seeing here, I also mark on G0 and A0. So A is this decreasing sequence. G is this strictly increasing sequence. Perhaps if I just put on another term, you can see hopefully these two are going to coincide in the middle somewhere, and this should help us find the limits. Okay, so I've assumed here that x is greater than y, so let's just have a quick look at what would happen if x was less than y. Then your A0 will be all the way over here on the left. Your A1 would still be the number in the middle between these two. Your G0 will be over here on the right. Then your G1 would still be somewhere around here. So what you'll actually find is from here, to find G2, for example, this will be partway between G1 and A1. And then to find A2, this is going to be somewhere, it's halfway between G1 and A1, so A2 would be around here. And then if I just draw on what's happening with the arrows, so initially your A sequence would increase and then it would start decreasing very quickly. Whereas here, initially your G sequence would decrease, then it would start increasing. So you have this initial kind of crossing over, but actually once this has happened after your first term, you've got this nice increasing, this nice decreasing property here. So let's deal with the limits now at long last. And how we're going to deal with this is using the monotone convergence theorem. Because if you notice, G is a strictly increasing sequence, and it's bounded from above by either x or y, so bounded above by the maximum of x and y. And you'll also notice that A, our sequence here, is a strictly decreasing sequence which is bounded below. So if you have an increasing sequence which is bounded from above, this has a limit. So this tells us that the limit n goes to infinity for increasing sequence Gn exists, and then we can call this L. And then similarly for a decreasing sequence bounded from below, this also has a limit. So a decreasing sequence bounded from below. So here our AN sequence is decreasing, it's bounded from below by the minimum of x and y, and this has a limit. So we can say that, therefore, the limit as n goes to infinity, AN, we call this L prime, this also exists. But I can go further than just saying that both of these limits exist. And this is where this example of the two sequences gets really interesting. So the limit as n goes to infinity of AN, well, I know that AN, this is going to be the same as AN minus 1 plus GN minus 1. So let's rewrite this as the limit as n goes to infinity AN minus 1 plus GN minus 1 all over 2. Well, we know that both of these sequences have limits, so we can use algebra of limits here. So this is actually equal to L dash plus L over 2. But then we know that the limit as n goes to infinity of AN, this is our L prime. So L prime is equal to L prime over 2 plus L over 2. So this tells us that if we subtract L prime over 2 from both sides, L prime over 2 equals L over 2. And therefore, L prime is equal to L. So we can conclude here that the limit as n goes to infinity of AN is equal to the limit as n goes to infinity of our sequence Gn. So this is really nice. We've started with two distinct numbers x and y. Basically we keep finding the arithmetic mean of the previous term in each sequence, and then for the G sequence we keep finding the geometric mean of the previous term in each sequence, and then eventually our limits will coincide here. So basically we don't know exactly what this limit's going to be. There's no particularly nice way of calculating it, but we know that this limit exists and these two do coincide. So the payoff of showing that these limits exist and are equal is that these this common limit gives rise to something called the Arithmetic-Geometric Mean of two numbers x and y. So you can also call this the AGM of x and y. So as a payoff of showing that this thing exists, we'll have a look at a couple of properties quickly. So the Arithmetic-Geometric Mean is symmetric. What that means is the AGM of x1 and y is the same as the AGM of y and x. And you can see this because if you imagine you've got different A0 and G0, you just swap your x and y around. But here, A1, this would be equal to x plus y. Here, A1 would be equal to y plus x. And both of these divided by 2. And here, G1, this would be equal to root xy, whereas here, G1 would be equal to root yx. Of course, x plus y, y plus x, these are equal. Here, root xy, root yx, these are also equal. So this is symmetric. It doesn't matter which way round you have your x and y. So another property we'll have a look at here then is if we kind of try and extend the definition a bit. So initially, we assumed that x and y aren't equal. What would happen if you had the arithmetic-geometric mean of x and itself? Well, kind of pictorially, your number line, instead of being between x and y, you would just sort of start at the point x. And here, you'd have a0 equals g0 equals x. a1, this would be equal to x plus x over 2. g1, this would just be equal to root x times x, so root x squared. This would be equal to x. So actually, an would be equal to gn, would be equal to x for all n. So what this means is the AGM of x in itself will be equal to x, which is a nice property to have. If you have any sort of mean of a number in itself, you should get that number back. So another property we'll have a look at, again, try and extend the definition a little bit here. What would happen if you had the arithmetic-geometric mean of 0 and y? So kind of on our picture here, if you imagine you have 0 and y, as your starting point, well, g of 0, this would be y, then g of 1, this would be the square root of 0 times y, which would be 0. So g would basically just be equal to 0. And then however many terms you go in, you'll find that gn is always going to be equal to 0. So a0, this would be equal to 0. a1, this would be equal to y over 2. You do 0 plus y over 2. a2 then, this would be y over 4, because you would do the arithmetic mean of y over 2 and 0. So kind of what happens with your a is you've got this decreasing sequence, which will just decrease down to 0. So here you can say your AGM of 0 and y is always equal to 0 for all y. So finally, let's have a look at one last property of the arithmetic-geometric mean, which is that it preserves scalar multiplication. So if you have the AGM of lambda x and lambda y, this is always the same as lambda multiplied by the AGM of x and y for all lambda greater than 0. And in fact, you can go even further to say that if you have an lambda, you call it, and if you call this gn lambda, so your two sequences where you've got the lambda inside, versus for this sequence, if you just call this an and gn as before, then in fact an lambda is always going to be equal to lambda an, and gn lambda is always going to be equal to lambda gn. And we can prove this by induction. So let's just start off with a0 lambda, g0 lambda, show that these are equal to lambda a0, lambda g0. So a0 lambda, this is the first term in this sequence, which is just lambda x. And then lambda x, well, this is just lambda times a0, where the first term in this sequence, because we've got x there, our a0 is just equal to x. So a0 lambda is equal to lambda multiplied by a0. And then similarly, g0 lambda, this is, your first term here is lambda y. But then your first term here is just y in the g sequence. So this is lambda times g0. So our inductive hypothesis then, we'll just assume that these are equal for n minus 1. So we'll say that an minus 1 lambda is equal to lambda an minus 1, and also gn minus 1 lambda is equal to lambda multiplied by gn minus 1. So now what we'll do is we'll try and prove that these are equal for all n using the inductive hypothesis. So now an lambda, so this is the nth term in the A sequence where we started with lambda. So what is this? Well, we just add together the previous two terms from each sequence and divide by 2. So this is an minus 1 lambda plus g n minus 1 lambda, all divided by 2. But then using the inductive hypothesis, we know that an minus 1 lambda is equal to lambda times an minus 1 for the other sequence, and similarly for g. So actually we can replace both of these straight away by this is equal to lambda an minus 1 plus lambda gn minus 1 all over 2. Then taking out a factor of lambda here, you'll see you've got lambda multiplied by an plus 1 plus an minus 1 plus gn minus 1 all over 2. And remembering your definition of what is your an, this is equal to lambda multiplied by an, where now this an is for this sequence without the lambda. And then we can do a similar calculation here for gn lambda, so the nth term in the g sequence where we've started with lambda x and lambda y. So this is going to be the square root of an minus 1 lambda multiplied by g n minus 1 lambda. But then we know from the inductive hypothesis we can write this as the square root of lambda an minus 1, where now this an minus 1 corresponds to the original sequence, just x and y, and multiply this by lambda g n minus 1, taking this from the g sequence for the original. Then we've got the square root of lambda squared, and take out a factor of lambda. This is lambda times the root of an minus 1 times gn minus 1, which is of course gn, just gn, isn't it, for this original sequence using the definition of where the next term comes from. So we've actually now proven this then, that an lambda is always equal to lambda an. We've also shown that gn lambda is always equal to lambda gn. So certainly you can say that the limit as n tends to infinity of an lambda, this is always equal to lambda multiplied by the limit as n tends to infinity of just an. And of course this is equal to lambda times the agm of x and y. And then when we started with this limit, this is equal to the arithmetic-geometric mean of lambda x and lambda y. So we've shown that this is equal to lambda times the AGM of x and y, which is what we were trying to prove there. So this AGM, the arithmetic-geometric mean, is indeed something which preserves scalar multiplication there.